There are two parts to this question, and other than them both being on matrices, they're not related. So I'm just going to focus on part one. We're told that A is self-inverse. That means it is its own inverse, and therefore, if we multiply it by itself, we are just going to get the unit matrix. We're asked to work out what value B is and the possible values for A. So we do not need to apply any kind of inverse formula here. All we need to do is, like I said, like times it by itself. So 2a minus 4b multiplied by 2a minus 4b is equal to, well, I'm just going to create this equation and then write my steps down equal to that. That means that 4, as I multiply it, then it will be plus a squared minus 4a. And then the next one along, 2a plus ab. And then 2a minus 8 plus ba minus 4b. Then a squared minus 4a plus b squared. Okay, and we want to solve for a and b. So I decided to, well, I think we have to actually solve for a first because it's this one here that only contains a. I can therefore set 4 plus a squared minus 4a equal to 1. And that means that a squared minus 4a plus 3 equals 0. So a minus 1, a minus 3 is 0, a equals 1 or 3. And we can sub back in. So I subbed it back into this one. So 2a plus ab is equal to 0. A equals 1 means that 2 plus b equals 0. So b equals minus 2. And then if a equals 3, then 6 plus 3b equals 0 and b equals minus 2 again. And I don't, we've been told that it's self-inverse, so we know that the rest of it is all going to figure out. We don't need to substitute back in to show that it's 0 and 1. Absolutely fine. We found it. We've done a equals 1 or 3 and b equals 2. So now we're asked to show that the invariant points of the linear, A represents a linear transformation M, and using the smaller value of A from part A, that's our 1. Let me just write that down. I'm going to get A equals, and then it becomes 2, 1, minus 3, minus 2. I'm then told that this has some invariant points, and they form a line. So just a little reminder, invariant points are where you take a point, you multiply it by your matrix, you're doing a matrix transformation, and it stays exactly where it is. What we can do is we can take coordinate or position vector x, y. When we multiply it by the matrix, it goes back to being x, y. That's why it's invariant. And if I multiply this out, I'm going to get 2x plus y equals x. I can just get rid of the matrix bit now, write it as a set of equations. And then minus 3x minus 2y equals y. The top one becomes y equals minus x, and the bottom one becomes 3y equals minus x. Just write down 3y equals minus 3x, which means that y is minus x there as well. So it's all consistent. If it wasn't, then we'd have no invariant points, or like just some maybe. Like if I had y equals minus 3x, and I think the origin would be the only invariant point. So actually, any point along this line here for this particular matrix would be invariant. And yeah, that's our answer. Just need to underline it. Let's take a look at the second part of this question. So now we're given a matrix P. This represents another linear transformation. Okay, then we're told that the triangle T has vertices, and I'm going to sketch this out, I think. So at 1, 2, at 3, 2, and then at 2, 5. Then we're told that the area of the image of T under this linear transformation is 15. And we're asked to determine the value of P. So, right, the original triangle was had a base of 2, and if we're going from 2 to 5, it had a height of 3. So the area of the original is just a half times 2 times 3. It's going to be 3. And then the area of the image is 15, which means that the scale factor is going to be 15 over 3. It's 5. It's got 5 times as big. By the way, it doesn't mean that they're similar or anything, but it is a fact that it's got 5 times as big. And it's also a fact that that is equal to the determinant of P. So det P is going to equal 3P squared minus 2P, so plus 2P, and that is equal to 5. So I can then do 3P squared plus 2P minus 5 is 0. Okay, let's try and factorize it. So I'll put a 5 here and a 1 here, and it'll all work out. I'll put a plus and a minus. So P is equal to minus 5 over 3, or 1. I'm going to reject this one because it says that P is a positive constant, and therefore P is just going to equal 1. Now, part B. So the transformation V consists of a stretch of scale factor 3 parallel to the x-axis. So by the way, that would just be 3, 0, 0, 1. That would just multiply your x by 3 and your y by 1 with the y-axis invariant. So I missed that bit. Followed by a stretch scale factor minus 2. This would be when I keep x the same. Minus 2 parallel to the y-axis with the x-axis invariant. And then the transformation V is represented by Q. So Q is the product of these, which just actually becomes 3, 0, 0, minus 2. And you can write this straight down. I was just trying to kind of do it step by step, but you might be able to see that that is essentially what it ends up being. And then given that U followed by V is the transformation W, which is represented by R, find the matrix R. So just got to get the ordering correct here. So U is first, and let's just remind ourselves, U was the transformation that came from P when we know it's equal to 1. So it's going to be 1, 2, minus 1, 3. And that one is first. So it goes on the right, and then I'm going to be multiplying by the second matrix. So this is my my V, 3, 0, 0, minus 2. And I should have probably added that is what R is equal to. Okay, just got to figure that one out. So it's going to be 3 times 1 plus 0, so just 3, then 6, then 2, and then finally minus 6. Well done on this question.